Okay, good morning. Two more topics remaining in chapter two. Short ones, not that big. One is the source transformation based on Thevenin Norton, and then the second one is maximum power transfer. Okay, and then we'll begin chapter three. Okay, source transformation. Source transformation is derived from the fact that the Thevenin and Norton equivalent circuits are both a representation of a large single circuit, right? So both the theorems state that you have a large linear circuit with multiple sources and multiple linear components. You can represent the entire circuit as a single voltage source or a single current source. Now, if A equals X and B equals X, we can state A equals B. So it's the same principle here. We can state that both the images, I'm sorry, not both the images, both the sources can be transformed into each other. The condition being that the voltage source must have a resistor in series and the current source must have a resistor in parallel. That is the representation of the Thevenin and Norton equivalent circuits. So if you perform a source transformation, you can actually simplify your circuit and avoid using a more complicated technique like node voltage analysis or mesh current analysis or even superposition. Okay. The equation governing the transformation is Ohm's law, because we have VTH is IN times RTH, right? So the equation governing both transforming from voltage to current and current to voltage is simply Ohm's law. Okay, still writing it down. Okay, quick example. Here we have a circuit in figure A, which has a voltage source and a current source. If you were to try to solve this, you would use either superposition, right? Perform two individual analyses, or node voltage or mesh current analysis, right? Again, this is a very simple representation of a two-source circuit. But we see that the conditions are met here. We have a voltage source, and the voltage source has a resistor in series, and we have a current source, and the current source has a resistor in parallel. So if you wish to transform this, we have to break the voltage source and or the current source along with that resistor and separate it out from the circuit, transform it, and then plug it back into the same place. So I'll call this A, call this node B. If I transform this current source into a voltage source, I get circuit B. And if I transform the voltage source into a current source, I get the circuit shown in C. Okay. So the way it would work is like this. You would break away the voltage or the current source by noting the two nodes where it is connected in place. So the voltage source and the resistor in series, which is R1, 5 ohms, 20 volts, are disconnected from the nodes labeled A and B. Okay, disconnected from the nodes that are labeled A and B. And then on the other side, of course, we have the 1 amp current source in parallel with R2. Again, the nodes, of course, are A and B. So far, so good. Any questions? Now we want to transform this. So let's take a look at the right side first. If you take a look at the current source and you transform it, we need to make sure that we plug it back between those terminals. So I'm going to draw out A and B, transform the current source into a voltage source, and then a resistor or the same resistor in series, right? So it'll still be R2 and 10 ohms. This will still be A, this will still be B. And from Ohm's law, I have R, I have I, 10 times 1 gives me 10 volts. And so it becomes a 10 volt voltage source between the terminals A and B. And then you can plug it back into the circuit. But it's a little tricky. Even sometimes I make mistakes if I try to use this as a technique. Okay, because trying to recognize those nodes and breaking it out, especially if the sources are somewhere in the middle of the circuit, it's very, very tricky to take them out and then plug it back in. All right, any questions on this one? Yes. That comes from here, the Thevenin and the Norton circuit. So Thevenin is a voltage source in series with a resistor, and current source would be in parallel with the resistor. And so when you transform the current source, you need to have a resistor in parallel with it. Otherwise, you cannot perform source transformation. And if you're trying to transform a voltage source, then you need to have a resistor in series with that voltage source. Otherwise, we cannot transform it into a current source. So again, as I said, the requirements have to be met before we actually even think about applying source transformation. It's a very useful technique because it can simplify your circuit to a very large extent. But again, it's in many ways it's complicated because recognizing which components are in series and parallel and then breaking it away from that circuit, that requires a lot of practice and a lot of experience. Yes. Yes. So question asked was about 10 volts. 10 volts is from Ohm's law. So we have the 10 ohm resistor and we have the 1 amp current source. So that gives us 10 volts. And if you plug it back into the circuit, we get circuit number B. And now if you look at circuit number B, you can see how simple it has become. We can simply add up the two resistances because they are in series, so it becomes 15 ohms. And you have two voltage sources. You can apply KVL and Ohm's law to solve for the currents and voltages for that resistors. Right? You apply KVL, 20 minus 10 gives you 10 volts across the 15 ohm resistor. Apply Ohm's law, you can find the total current I that is flowing through the circuit. Once you have the total current I, you can find the individual voltages across each one of those resistors. So instead of writing out multiple equations for node voltage analysis or mesh current analysis, simply 2 or 3 step answer. Make sense? On the other side, if we take the voltage source, we can transform it into a current source. The direction, of course, remains the same as the sign of that voltage source. That still remains as A. This becomes B. R1 is 5 ohms. And current direction pointing up. Using Ohm's law, I have 20 volt source and a 5 ohm resistor. So I would have a 4 amp current source. And if I plug that back into the circuit, you get circuit number C. Circuit number C. And again, circuit number C, again, you can see. Now you can solve circuit number C using KCL and Ohm's law. Make sense? Any questions? Okay, then let's look at the last topic, which is maximum power transfer theorem. Electronic circuits, electronic devices often have multiple cascading circuits connected one after the other. And start writing down previous. Okay, hold on, here we go. Done? Okay. All right, so as I was saying, oftentimes electronic devices have multiple circuits connected in a sequence. One common example I like to use is a audio circuit or audio video receiver that would have a preamplifier stage, more commonly known as a preamp. And the output of this preamp is connected to the main amplifier stage or main amplifier circuit. And the output of the amplifier goes into a speaker. The speaker, of course, is also a load. It's a resistance. It's also a circuit, a simple one. But every succeeding stage is being driven by the preceding circuit, meaning power from the first stage goes to the next, from the first to the second, from the second to the third, right? And this is just a simple representation, but there are larger circuits with billions of transistors. Then there are like hundreds of thousands of stages, right? Thousands of individual circuits. So depending on your requirement, you want either maximum power to be transferred from one stage to the next, or you want maximum power efficiency to be transferred. Well, if you want maximum power to be transferred from the first stage to the next one, the theorem states that the succeeding or the second circuit should have a resistance that matches the Thevenin resistance of the preceding circuit. So in this example, let's say there is a large circuit of comprising of sources and resistances. You would represent this using its Thevenin equivalent circuit. Right? That large circuit could be anything. Again, in this example, let's say it's a preamplifier. Then the Thevenin resistance of that preamplifier should match the Thevenin resistance of the amplifier. Again, the input resistance, sorry, not the Thevenin resistance. The Thevenin resistance of the preamplifier stage should match the total resistance of the amplifier stage. And then the output or the Thevenin resistance of the amplifier should match the resistance of the speaker. Real life example, if you go online, you can download the manuals for any manufacturer, any make, any model of amplifiers or audio video receivers, and also look at the specifications of a speaker. If you look at the specification, it will always state the amplifier can supply certain amount of power, like say 100 watts, into a 4 ohm speaker or a 8 ohm speaker. And what it is trying to do is the output of the amplifier, the Thevenin resistance of the amplifier is 4 ohms or 6 ohms or 8 ohms. And so the speakers that you choose should match the resistance of that amplifier. Okay, so if you're self-installing a system, that is something that you need to keep a lookout for. Okay, if it's a pre-built home theater in a box, the speakers are already matched. Headphones need a lower volume, they need lower current so as to not load your mobile devices. So wired headphones have impedance of about 32 ohms, at least if your phone has a headphone jack nowadays. So again, as I was saying, the Thevenin resistance of one circuit should match the resistance of the succeeding stage. And in that case, maximum power will be transferred from one stage to the next. RL, meaning the load resistance, should match the Thevenin resistance of the preceding circuit. RL here is simply noting the load resistance. Okay, load resistance. And the maximum power can be derived by, again, applying Ohm's law and then applying the power equation. Power, of course, is given by V square over R. So you find the current in that circuit, and then you apply the equation, and the resulting equation is PL max V square over 4 times RTH. Okay, 4 times RTH. Now, maximum power does not mean maximum efficiency. Okay, maximum power does not equate maximum efficiency, meaning power will be lost. Maximum efficiency is not achieved at maximum power. But depending on the application, of course, sometimes you want maximum power to be transferred, sometimes you want maximum efficiency, right? If you are, let's say, electric vehicle, right? If you're driving an electric vehicle, sometimes you might want maximum power, but then that's not maximum efficiency. So you would use up a lot of your energy from the battery. Actually, it doesn't matter whether it's an electric vehicle or a normal vehicle. It doesn't really matter. But if you want maximum power, you're going to use up a lot of fuel, a lot of energy. So it's inefficient at that time. But if you want maximum energy, meaning maximum mileage, then your power might not be at max. Yes. Yeah, depends on what kind of system it is. Thermal loss mostly. Yeah. It's like not an exact comparison, but let's say you're driving down the highway. There's a certain speed at which your vehicle would give you maximum mileage. If you exceed that, you would have high speed, but you're burning more fuel. So the return that you get by burning more fuel, you might get more speed, but it won't result in a good mileage, if that makes sense. So not an exact analogy, but I find it's useful. Does that make sense? Kind of. Okay. All right. So that is the end of chapter 2. There aren't any problems that I give out for source transformation or for maximum power transfer. It's a technique that we do use. There is an extra credit problem on the homework, which hopefully you did last night, or maybe you might be doing today or over the weekend. So go over the tutorial, it's extra credit, and that will help. This will help you do that, solve that. Maximum power transfer is an important component of lab 4. So if you've not yet done lab 4, that's where it's coming up. Okay, maximum power. So you will actually apply voltage, and you will measure the power, and then you would create a chart in lab 4. Some labs, especially the ones on Monday and Tuesday, are ahead. So several students in those labs did send feedback that lecture is like behind or anything, but I would like to state the lecture is actually on time because lab 4 is not scheduled until next week. So we are ahead of lab 4, but unfortunately we have a Monday holiday in May. Every quarter we have like 2. This quarter we only have 1. But because of that Monday holiday, the Tuesday after that holiday follows a Monday schedule. So we lose 1 Monday and we lose 1 Tuesday. And so if the lab is on, well, actually, yeah, we lose a Monday. No, what am I saying? We lose a Tuesday. So if your lab is on a Tuesday, then unfortunately, you lose 1 week. To make up that material, some instructors start the lab in the first week itself. What compounds the problem is you are now a week ahead of the other labs, but also you are ahead in the week itself. So if your lab is on a Thursday or a Friday, then you have classes on Monday, Wednesday. It makes up time to actually learn that material. But if your lab is on a Tuesday, it's early in the week, and you're also 1 week ahead, it's not possible for the lecture class to cover that material a week and a half in advance. But that's the reason why the lab write-ups are so detailed. Okay, there's a background theory section, which most students don't read. But that background theory section covers everything a student needs to know about that lab itself. Okay, it also covers all of the equations that are required to solve for that lab. Okay, so if you have that, please read the lab write-up and then reach out to your instructors, the lab instructors, and your 3 instructors. Okay. Anyway, so that's the end of chapter 2. These 2 are the most important chapters for the entire class, right? Chapters 1 and 2. If I was to summarize, everything is based only on 3 equations: Ohm's law, KVL, and KCL. Those are the only 3 equations you need to really remember. Everything else is derived from these 3 equations. Voltage division is derived from Ohm's law. Current division is derived from Ohm's law. Node voltage analysis is a combination of Ohm's law and KCL. Mesh current analysis is a combination of Ohm's law and KVL. Thevenin and Norton is not an analysis technique. It is simply a concept. So again, the 3 equations that you need to remember are just KVL, KCL, and Ohm's law. Everything else is a technique. It's a concept. Okay, how you apply the concept, that is the most important part. So let's go to chapter 3, where we will learn about inductors, capacitors, and their function in electric circuits. From what I understand from the physics classes do cover a little bit of inductors and capacitors, right? At least some of it. Do you remember the equations? Okay. Inductors and capacitors are both energy storage devices. Like a resistor, an inductor and a capacitor is a passive component. Okay, it does not have any energy of its own. It's a passive device, but a resistor cannot store any energy. It simply receives the energy and dissipates it as heat. Electrical energy converted into thermal energy, right? So resistors do get hot depending on how much current is being transferred. Capacitors and inductors, on the other hand, are energy storage devices. They do not have any energy of their own, but they can receive energy, they can store energy, and they can release the energy back into the circuit at a later point in time. Okay, so if energy is being transferred to an inductor or capacitor, there is, of course, a certain amount of heat that is also generated and lost, but primarily they store the energy and they release it back into the circuit at a later point in time. When I say later point in time, it does not mean like days or hours. It's sometimes milliseconds or microseconds, very, very quick. because most capacitors and inductors that we encounter in real-life electronic circuits are very, very small, very tiny. Femtofarads or picofarads, 10⁻⁻⁶, 10⁻⁻12, 10⁻⁻15. Okay, very, very small. So I like to use the analogy of a bucket. If you have a bucket, you're trying to fill it with water. The size of the bucket, the flow of the water, and the dimensions of the pipe and the tap all govern the speed at which the bucket fills up and the speed at which you can empty it out. Okay, so the inductor or the capacitor is the bucket. The electric current that is flowing through the conductor is the analogy for the water or the fluid and the pipe. Okay, the size or the dimensions of the pipe will be equal, not equal, but analogous to the resistors that are present in the circuit. So when we look at these equations, they will all encounter, you will encounter the size or the value of the inductor and the capacitor and the value of the resistors that are permitting the current to flow through. The energy that comes into an inductor is stored or associated with a magnetic field. The energy associated with the capacitor is the electrostatic field or the electric field. Okay, we will stay on this side of engineering. We will not go into the physics of things, not a lot. I will explain a few basic things, but we will not go into the physics, right? We will stay on this side of the engineering. We'll stay on this side of the line, stay on the engineering side. In chapter 3, we will look at the standard equations that govern, standard equations for the voltage, the current, the power, the energy for the inductor and the capacitor. In chapter 4, what we will look at, again, we will look at the capacitor and inductor, but chapter 4 will look specifically at a small portion of that transfer. Okay, so I'm saying, right, it's an energy storage device, so energy is transferred into the component and then back out of the component. Okay, but that energy transfer cannot take place in an instant. Thanos is not snapping his fingers. Energy transfer will take a finite amount of time, again, depending on the size of the bucket and the flow of the water, right? So it will take a finite amount of time for the energy to come into the component and then come back out of the component. That energy transfer phase is very, very small. Again, as I said, components are small, so the energy transfer is small. Milliseconds, microseconds, even nanoseconds. Okay, very, very quick, very, very fast. But that energy transfer phase is what we will look at in chapter number 4. And that's why I said small portion. When I say small portion, does not mean small analysis, but a small portion of that energy transfer phase. Chapter 3 will look at the generic equations. Chapter 4 will look at a small portion of that analysis. So let's look at inductors first. As I stated, inductors store energy in the magnetic field. Magnetic field relies on magnetism. Magnetism is a big part of every electronic device that we use today. Okay. Common examples are generators, motors, transformers. Generator is a coil that rotates in the magnetic field that generates electricity based on either, that the mechanical movement of that coil can be either wind, can be water. Some mechanical energy is converted into electrical energy. And that's what a generator is. Transformer is 2 coils wound up together inside the same core. Okay, these are not Michael-based transformers. These are electrical transformers. You would have seen them on light poles. There's a big cylinder surrounding a light electricity pole, right? And then there's a distribution box that goes into each residence. Right outside, let's see, there's a power plant here, but if you go down the walkway towards Dexter Lawn, there is a wooden fenced area which says high voltage, do not enter. That is a transformer. High voltage lines are coming in and being distributed out. So these transformers are nothing but inductors. They are like 2 inductors wound together, and the phenomenon is known as mutual inductance. How many of you have wireless charging phones? Anyone? Most of you might have wireless charging phones. The back of your phone has a coil. That coil is an inductor. Your wireless charger, the plate, has a coil. When you bring the phone in contact with that wireless charger, the coils, which have magnetic fields, they interlink. Energy from your wireless charging plate is now sent through the magnetic fields into the wireless coil of your phone. It's a real life example of where you're actually using mutual inductance. So again, electromagnetism, very important part of everyday life. There were several researchers who worked on electromagnetism over centuries. Some of the most famous ones are beginning with Ampere in the early 1800s. He came up with what is known as Ampere's circuital law. And then following his work or publication of his work, you had Carl Gauss, Michael Faraday, James Maxwell, all of these researchers. There were hundreds of researchers who were working, but these are the ones who became famous. And then, when you are the early ones who publish, it comes to, your names become famous, stuff is named after you. And so these researchers have, have units and components named after them. Like Ampere, of course, is the unit for current, right? Michael Faraday has capacitor units named after him. Okay. Maxwell's equations are basically the foundation of the field of electrical engineering. So Maxwell's equations are very important for electrical engineering. Anyway, let's start with what a magnetic field is. Again, staying on this side of engineering and not going into the physics. Every wire, every current carrying wire, actually, let's back up. Every wire, whether it carries current or not, inherently has resistance, capacitance, and inductance. If I take this power cable or the HDMI cable, it has resistance, right? But the resistance does not rise to the level of interference. The job of that cable is to transfer 120 volts from the power outlet to the adapter. So 6 feet of cabling has resistance, but it does not interfere with its function. So we don't really care about it, right? In the same way, it also has inductance. Current is flowing through that wire, so there is a magnetic field that is present around that cable. But that inductance does not rise to the level of interference. It does not interfere with its job of carrying the electric current. So when current flows through a wire, a magnetic field is established around that wire. And magnetic field is in the form of magnetic flux lines. Okay, magnetic flux lines. Those flux lines have no beginning and they have no end. They are circular. We can use the right-hand rule to determine the direction of the magnetic flux lines. Basically, if you take your right hand and you coil it around, the thumb pointing in the direction of the arrow or the current, and then your fingers would point towards the magnetic flux lines. So next time you're charging or you plug an adapter into the wall, power is coming from the wall outlet and going through the wire. If you just point your thumb out towards the direction of the current, then your fingers are pointing towards the magnetic flux lines. If you take that same current carrying wire and you wind it up in a coil, those magnetic flux lines are now pointing in that same direction and outward through the center of that loop. Okay, so the magnetic flux lines get aligned and they all point in the same direction out of the center of that loop. If you wind up that coil into multiple loops, creating a spiral, the magnetic flux lines align and now also establish a line that goes to the center of that spiral coil. And again, it is kind of a continuous loop. It has no beginning and no end, but it mimics a magnetic field with a north and a south pole. Okay. So that magnetic field mimics a magnet with a north and a south pole. This magnetic field is very weak. Okay, depending on the amount of current that is flowing through and other physical parameters, this magnetic field is weak. It is present, it is there, it is established, but it is very, very weak. If you insert a magnetic material through the center of that coil, the magnetic field is enhanced. It becomes stronger. The principle is that a magnetic material allows the flux lines to be established very easily. Okay, it allows a structure, if you will. It allows a structure, a scaffolding for the magnetic flux lines to be established through it very easily. And that is the working principle of an electromagnet. You have a magnetic material, which is not a magnet by itself. It simply allows a magnetic flux lines to flow through it very easily, to be established with ease. And you wind a coil around that material. When you flip on a switch, current flows through that wire. It now becomes a very strong magnetic field. Because it is based on electricity, it is now known as an electromagnet. And if you recall, you might have seen either pictures or videos of big, heavy cranes picking up vehicles with electromagnets. And so the magnetic field established is very, very strong, sometimes even stronger than a permanent magnet. So again, that's the working principle of an electromagnet. Okay. That would be known as the core because it's going to the core of the spiral loop. Okay, let's look at the physical construction of an inductor. Sorry, not physical. Let's look at the symbols. So a current flowing through a coil establishes a magnetic field. That component is known as an inductor. It is labeled or noted as uppercase L. So uppercase R notes resistance. Uppercase L indicates it's an inductor. Okay, inductor. The unit is named after Joseph Henry, an uppercase H. I should have said it's named after me, but that's not really true, of course. All of these are uppercase. They are not lowercase. Okay, so resistor R is uppercase, inductor L is uppercase. Ohms, of course, is the symbol omega. But capacitor is C. You'll see that in next class. And then the unit for inductor is uppercase H. Capacitor is farads, uppercase F. So they're all uppercase. And the symbol is just a spiral coil. Like a resistor, you can draw it horizontally. You can draw it vertically, depending on the circuit condition, circuit needs. Okay. And like a resistor, an inductor is also a passive component. Capacitor is also a passive component. So it follows the passive sign convention or the passive reference configuration. Okay. It follows the passive sign convention or the passive reference configuration. Meaning when current flows through an inductor, the point of entry would create a voltage that is positive, point of exit is minus. Okay, and you can see that here. Point of entry is positive, point of exit is minus. Tail end of the arrow will always be positive. All right, let's take a pause. Let me know if you have any questions thus far. Any questions? Okay. Physical construction of an inductor. Okay, it's simply a conducting piece of wire that is wound in a spiral coil. The center of that coil is known as the core. If there is no material present in the core, we say it is an air core inductor. Right? Air core inductor. The length of the coil is measured from end to end. So this lowercase l is the length of the inductor. Every loop is counted as a turn. So every loop is counted as a turn, and the number of turns is directly proportional to the inductor value. The equation is given by L mu n square A over L, where A is the cross-sectional area. Cross-sectional area of the core or of the coil. Okay, cross-sectional area of the coil. Mu is defined as the permeability. Permeability, again, is the ease with which a magnetic flux line can be established through the core. It is given by mu 0 and mu r, the product of mu 0, mu r. Mu 0 is the absolute permeability, is a constant, 4 pi into 10 raised to minus 7. And mu r is the relative permeability of the core material when compared to mu 0. Okay. Mu r is relative permeability. So again, mu itself is a product of mu 0, mu r. It defines basically the ease with which you can establish magnetic flux lines through a material. Now, if you take a look at the coil is made out of a conducting piece of wire. Okay, a few seconds. We'll take a pause while everyone writes it down. Okay, so as I was saying, if you take a look at the image or the illustration, it's made up of a conducting piece of wire, right? A wire in real life does not have 0 ohm resistance. Depending on the material, depending on the size of the wire, it will have some resistance. That resistance is part of the coil. If you take this inductor and you measure the inductance, you will obtain a certain value. If you measure the resistance of this coil, you will again obtain a certain value of that resistance. Depending on the quality of the inductor and the quality of the construction, that resistance could be very small, like 5 ohms or less, or it would be quite large, like exceeds hundreds of ohms. So it depends on the construction. In the labs, the real life inductors we use are both of low as well as high quality. It depends on the purpose, it depends on the lab. So the way we represent this is as an inductor in series with a resistor. As I said, the same component, the same spiral coil, if you measure the inductance, will give you a value. If you measure the resistance, it will also give you a value. So it's physically it's the exact same component. We cannot separate out the resistance from that inductance. But electrically, if you're trying to perform a calculation or a simulation, we need to have 2 separate components. So we represent it as an inductor in series with a resistor inside a box. Okay, we cannot separate this out. We can measure it, we can manipulate it, but we cannot separate it out. And so if you measure from this end to this end, that represents that entire curve. The inductor portion is represented as L, and the resistive portion is represented again as RL. But this time RL is not load resistor, It is the inductor resistance. Okay. RL is the inductor resistance. This concept is heavily, you'll use this concept heavily in understanding lab number 6. Okay, if you're checking the lab, this is where you will need this concept. Okay. Okay, pause. Let me know if you have any questions. Right. One more point about this is that a real life inductor, if it's an ideal inductor, you could send some energy into the inductor, take the inductor out of the circuit, and you would expect it to hold its energy infinitely, right? But real life doesn't work that way. You charge an inductor, you take it out of the circuit, what will happen? It will discharge the energy slowly through itself. And that is represented mathematically and electrically using that resistance. You would say the inductor is charged, it forms a closed loop between its own terminals, and the energy is lost as heat through that resistor. Okay, the same thing happens with the capacitor also. So again, real life inductors will not be able to hold the energy infinitely. Then here are just some examples of inductors. I'd like to point out just 2 things, actually 3 things. So we looked at this equation, right? We see that the inductor is directly proportional to the number of turns, also directly proportional to the cross-sectional area of that wire or that coil, right? And then it's inversely proportional to the length, meaning if the length is high, the inductance will be small. So if you look at these first 2, right? Yes. Length of the coil. So starting at the end, so the question being asked is what is defined as the length? So it's not the length of the wire, but it's actually where the coil begins and where the coil ends. Good question. So here are toroidal inductors. It's the magnetic core is in the shape of a toroid. You can increase the length that way. But if you look at this wire, much thicker than the one in figure B, right? So if it's a thicker wire, the current carrying capacity of that wire is large. And you can see that in the specs. This inductor can carry 10 amps of current versus 1.3. 10 amps is a huge amount of current. Okay, huge amount of current. But the number of turns is far less. Inductor is directly proportional to the number of turns. Low number of turns, lower inductor value. High number of turns, high inductor value, 100 times. So even though the coil is thinner, the large number of turns allows a more stronger electromagnetic field. Also, the wire itself, because it's thick, the resistance is very, very small. Resistance R is rho L over A. It's inversely proportional to the cross-sectional area of that wire. So the thicker the wire, the lower the resistance. The thinner the wire, the higher the resistance. So here, 6 milliohm resistance versus 400 milliohms. Okay, 6 milliohms versus 400 milliohms. Just 2 things I wanted to point out, depending on the material, depending on the design, how the value of the inductor is different. And VI equation. Actually, it's 11 o'clock, so let me end right here. We'll pick up here again on Monday. Quiz as usual. Quiz will be based on Thevenin and Norton. I will not ask you to perform a full analysis. because again, full analysis is simply requiring analysis techniques, which we already assessed. What I will ask you is, you will look at multiple circuits and you will draw out the circuits that are required to solve for the Thevenin voltage, Norton current, and Thevenin resistance. That's what I will ask you to do. Okay, so no analysis or calculations, but basically you have to show me that you can understand the question being asked and then draw out the circuits that are required to perform the analysis. All right, I'll bid you a good weekend and I will see you all on Monday. If you have any questions, I'm open today from 1 to 2:30, actually 1 to 2 o'clock, 1 hour. Then I have a seminar and a workshop. So I'll be in my office till 5 o'clock. Stop by anytime between 1 and 2 or 4 to 5. Yeah.